Do we live in an artificial universe? It's a question that's inspired countless movies, books, and philosophers. Most people see it as sort of a thought-provoking sci-fi concept and nothing more. What if I told you this is a real possibility? Okay, you might say, I can wrap my head around that. Maybe we do all live in the Matrix. No one can really know for sure if the universe is real, but here's where it gets really crazy. What if I told you the prevailing theory supporting an artificial universe not only postulates that nothing we currently experience is real, but in fact our entire universe is nothing but a 2D projection of a 3D universe? Mind blown. You might be saying, now wait a second, our entire universe is three-dimensional. Everything has a length, a width, and a height. That's where the holographic principle comes in. You've all heard of a hologram before. It's a 2D image that when projected appears to be 3D. No one questions that a hologram looks 3D, but no one would argue that it is, in fact, 3D. The holographic principle states that our universe could be the same way. We just don't have the observational tools yet to know for certain. How did this theory come about, you ask? Well, it all started with a dispute between Leonard Susskind and Stephen Hawking called the Black Hole War. Obviously, you'll know who Stephen Hawking is, but you probably don't know who Leonard Susskind is. It's a shame, because he's a pretty smart guy. Anyway, Stephen Hawking said that when energy goes into a black hole, it disappears forever. Although this sounds contrary to the first law of thermodynamics, it actually makes sense when you factor in relativity. Now, this disturbed Susskind, to say the least, because he was a quantum theorist. If Hawking was right, Susskind and everyone else could kiss quantum physics goodbye, at least quantum physics as we know it. So Susskind argued that no, the energy must be conserved in some way, even though it doesn't look like it, and this is called the black hole information paradox. So Susskind and Hawking were fighting about this from 1981 until 1994, until Susskind actually proved that he was right. That's right, this guy actually proved Stephen Hawking wrong. Someone give this man a raise. If that wasn't good enough, Susskind also proposed the holographic principle, which would account for the seemingly paradoxical behavior of black holes. But he didn't really have the concrete evidence to back it up at the time. Oh, and he also helped found string theory. What did I tell you? Pretty smart guy. That's where a story about the black hole war ends. Oh, and don't worry about these guys, by the way. They're friends now. The real evidence didn't come until 1997, when a theoretical physicist named Juan Maldacena discovered that the equations that describe the gravitational theory are the exact same that describe quantum field theory, albeit a very specific type of universe. Now to clarify, gravitational theory describes the movement of 3D objects in what we know is our 3D universe, while quantum field theory describes the movement of subatomic particles in a 2D universe. This hypothetical universe in which these fields intersect would be an anti-de Sitter space, which looks kind of like this. And needless to say, our universe is not an anti-de Sitter space. It's a more or less flat space. In fact, anti-de Sitter space is pretty much completely irrelevant to flat space. However, it did open up a link to apply the holographic principle to our universe, because it provided a link between 2D and 3D universes that was completely unexpected. It wasn't until just last year that this link was found to have an application to our universe by a team of theoretical physicists at the Vienna University of Technology. These equations don't match up perfectly for everything in the case of flat universes. They do match up when it comes to quantum entanglement. Quantum entanglement is the combination of two quantum particles. When quantum particles are entangled, they form one system, regardless of the physical distance separating them. Just how entangled two particles are is measured in the entropy of entanglement. And here's the interesting part. You can measure the entropy of entanglement using either gravitational or quantum field theory in a flat universe. Though it's certainly not proof, this is certainly compelling evidence for the holographic principle. At this point you might be wondering, but all of this is theoretical. Where's the physical evidence? Well, that's exactly what scientists at Fermilab are looking for. Failing hypothesis is that if our universe is indeed a hologram, there would be limits to how much data the universe can store, and we should be able to find signs of these limits. They're sort of like glitches, if you prefer to see them that way, although they've officially been termed holographic noise. Fermilab is using a device creatively termed the holometer in order to detect this noise. Now, as promising as all this seems, the holographic principle isn't infallible. You may know that we don't really have 3 dimensions, we have 4, and some physicists are even arguing that we have more than that. But holographic theory doesn't yet account for time or any of the other factors. But who knows? That may change in the future with further research. The real interesting thing about the holographic principle, and this is mostly the reason I chose to talk about it, is the questions it raises. If we are in a 2D projection of a 3D universe, then how incredibly complex must that universe be? Would there be life, perhaps even intelligent life in that universe? If so, and I know this ventures in sci-fi territory a little bit, could this higher form of life purposely control the projection? Could the 3D universe be a projection itself, so it could be projectionception? And perhaps most importantly, what would we do if we found out that the holographic principle applied to our universe? These are questions that we may never be able to answer, but they're certainly fascinating to think about. So, to conclude, do we live in a virtual universe? You may never know for sure, but it's more likely than you think.